Invisible ripples of high-energy distortion are constantly washing over Earth. They pass right through us, traveling at the speed of light, carrying the echoes of some of the most violent collisions in the universe. We couldn't detect them until 2015, but since then, sensitive ground-based instruments have caught dozens of these signals. By measuring the tiny disturbances inside these 4-kilometer-long concrete beam tubes, astrophysicists proved that stellar mass black holes are colliding out in deep space. Curious, but finding them created an immediate physics problem. For two black holes to spiral into each other and merge within the 14 billion-year lifespan of our universe, they have to start their orbital dance incredibly close together. The issue is where these black holes come from. They are the collapsed remnants of massive stars, and those dying stars dictate their starting positions. And those parent stars are enormous. If two stars were born close enough to eventually merge as black holes, their outer layers should have completely swallowed each other long before they ever ran out of fuel and died. At the end of its life cycle, a massive star doesn't quietly collapse, it swells. A star capable of leaving behind a black hole can expand to hundreds or even thousands of times the radius of our Sun. This chart tracks the maximum initial separation two equal-mass black holes can have to successfully merge. The vertical axis shows distance, and the plotted lines represent the absolute mathematical limit for gravity to pull them together within the age of the universe. The required distance is tiny. It's often a fraction of the physical volume taken up by the parent stars themselves. The geometry simply doesn't fit. The basic laws of stellar evolution suggest that the initial proximity required for black hole collisions should be physically impossible. Astrophysicists have identified a few specific mechanisms that bypass this problem. The first is a process called isolated binary evolution, which starts with two stars born far enough apart to give each other room to grow. Tracking this diagram from top to bottom, the larger dying star expands, completely engulfing its companion in a common envelope. Inside, friction from the shared gas acts as a massive brake, violently shrinking their orbit until the envelope is ejected, leaving two tightly packed cores. There is also a second isolated model, shown here. Notice the lack of stellar expansion in these middle steps. In this chemically homogeneous evolution, intense internal mixing prevents the stars from swelling up in the first place. Whether through a violent shared envelope or rapid internal mixing, the universe manages to strip away the bulky stellar material, leaving bare, dense cores perfectly spaced for a future collision. But stars don't always form in neat, isolated pairs. Our second major pathway happens in extremely dense environments, like globular clusters, where millions of stars are packed tightly together. In these crowded spaces, the heaviest objects naturally sink towards the center. When massive stars collapse into black holes, they migrate into a chaotic core, setting the stage for close encounters. When an unbound star wanders too close to an orbiting pair of black holes, the three masses engage in a complex gravitational dance. The binary catches the interloper, ejecting it at high speed to shrink its own orbit. Alternatively, a distant third body exerts a steady pull, the Kozai-Ladoff effect, stretching the binary's orbit into a highly eccentric oval that forces them together. Through constant scattering and gravitational interference, the cluster's chaotic dynamics act as a cosmic forge. They blindly force complete strangers into the dangerously close proximity required for a merger. Once gas friction or cluster dynamics force the black holes close enough together, the mechanics change completely. Gravitational wave radiation takes over as the dominant physical force. As the black holes orbit, they emit gravitational waves that carry away their remaining energy. The closer they get, the faster they bleed energy, causing their orbital speed to drastically accelerate in a final death spiral. We can track this final fraction of a second on this waveform chart. The sharp rising peaks show the plunge and merger into a highly distorted single shape, followed by a rapid decay, or ring down, as the black hole settles into a stable sphere. But the collision is rarely perfectly symmetrical. If the masses or spins are unequal, the merger emits a heavily lopsided wave pattern in one direction. To conserve momentum, the newly formed black hole recoils in the opposite direction like a gravitational rocket. This kick is incredibly powerful. The velocity can easily exceed the escape velocity of the host star cluster, ejecting the new black hole entirely into intergalactic space. The brief, violent chirps we detect in our underground lasers are the final echoes of a story that took millions of years to unfold. By decoding them, we can reverse engineer the hidden, chaotic choreography of the cosmos.